Hello guys, welcome to this segment of tutorials now wherein which we will be looking into the working of CNNs and we will be looking at coming up with a network for a classification task using MNIST dataset. Okay. So earlier in our tutorials we have just discussed regarding PyTorch, its functionalities, now creation of data sets, creation of simple MLP layers, the forward propagation, the back propagation, how it happens, the automatic differentiations, the gradients, different kinds of loss functions, optimizers, how to bring in together all of these ideas we just discussed in our earlier discussions of PyTorch. So now we will continue from the same point. Now here in this segment, now we will be looking into the convolutional neural networks, wherein which we will be mainly interested in now how does the internals of CNNs work. Okay. So now whenever we want to work with images, the go to lightweight networks that are used are CNNs. Nowadays we have VIT. Yes, we will look at VITs sometime down the line, we will for sure look at VITs. Now that is the reason why I use the word lightweight. Okay. Now in this we will be looking at CNNs. Now here now I have an input which is a random input. I have just taken a random input just for the sake of convenience as of now. So I am having a batch of 8 examples and each example is of size 3, 32, 32. Now this is this is the batch size. Now this is the number of channels in each of the image. Now this is the height and width of each of the ones. Now here so you have got 8, 3, 32, 32. Okay. So now let us look at how does this convolutions work. Okay. So now before that, now let us go into this a very nice GIF. Now this is from the Stanford CS231 website, now which is there. Now here now we can see that now these are the two filters are there. Now each filter has 3 components. Now why each filter has 3 components? The 3 components depends on how many in channels are there. Okay. So and then the output, the number of channels in the output depends on how many filters are there. Okay. So now you have 2 filters. Now therefore you have in the output you have 2 channels. Now you have 3 channels in the input, therefore in each filter you have 3 components. So and then at a time you are looking at a 3 cross 3 segment. Okay. Now this is looking at this 3 cross 3 segment, this 3 cross 3 segment and this 3 cross 3 segment is what is being looked into. Okay. Now what do? You perform element wise multiplication, add all of them. So you get a scalar from this operation, you get a scalar from this operation, you get a scalar from this operation through 3 scalars. So you add all 3 of them plus 1 this scalar. So that will give you this minus 1. Okay. Now you can see zeros here, this is the padding, you have gone ahead and went with 0 padding. Now you have done a padding of 1 layer, therefore you can see now the repetition of zeros at once. There are multiple kinds of padding, but most preferably the one that is being used is 0 padding. Okay. Now before padding each of the image size is 5 cross 5. Now you have 3 channels. Now therefore the pre-padded image size is 5 cross 5 cross 3. Post padding it is 7 cross 7 cross 3. Okay. So now let us make a note of that. So now here now we can see that the x which is the input that I have is a 5 cross 5. This is a 5 cross 5 cross 3. This is the height in, width in, this is d in. Okay. So and then you have padding, you have done 1. So 1 dimension of padding is what you have done, and then you have stride. Now that means that after each operation how much you are moving. Okay. You are moving by 2. Now as you can see from this example very clearly, now you are here. Okay. In this point once you go ahead you will be going with this segment of the image. Okay. Now as you can see here you have moved by 2 in x axis and the same thing will be moved, preferably we will use the same stride in x axis and y axis. Okay. So stride is 2 and then so you have the kernel size, okay. So the kernel size which is referred by f, which is 3 cross 3. Now most of the times we use square kernel, okay, unless specified we can use rectangular kernels as well, that is perfectly fine. And then how many filters are there? You have 2 filters, okay. So now you can think of it like this. Now how do you compute the number of weights in this case? Okay, you have 3 cross 3, that is repeated thrice because your input channel has, this is the kernel size, this is your D in, this is your kernel size, okay. This is repeated twice, this is your K, which is number of filters that are there. So 3 cross 3 cross 3 into 2, and for each of this plus 2, okay. Now these are the number of weights that are there that needs to be learnt in this particular convolutional operation. See, there is another way of looking at this. You can look at CNNs as a regularized MLPs, now wherein which you have weight sharing, okay, and then local receptive fields, okay. So that is another way of looking at CNNs. You can think of them, there is weight sharing. Now that means that for all the chunks we are using, okay. Now if I have a, let us say that I have 4 nodes here and then have 4 nodes here. Now you can say that, okay. Now this is the idea of local receptive field. Now this particular neuron that is there is only looking at these 2 locally, this is only looking at these 2, okay. This is the idea of local receptive fields. On the other hand, now if you say that now the weight which is there here, this weight is same as this weight, okay, and this weight is same as this weight. Now this is what is known as weight sharing. Now this can be looked at as regularizers, okay. Now we can look at the CNNs as a regularized MLP wherein which we have the local receptive fields and then weight sharing, okay. But that apart, now these are the number of weights that you need to look into, so which are there. Now given this input dimension and these hyperparameters, these are hyperparameters. So in MLP we have how many number of layers should be there, what should be the number of nodes in each of those layers and other things. These are hyperparameters that are there. Now here, now we can compute the output after this, the output will be, so H out cross W out cross D out. Now this is the output size which is there. Now how do you compute this given this? Now we can compute this. Now this H out equals H in minus F plus 2P divided by S plus 1, okay. Now similarly W out equals W in minus F plus 2P divided by S plus 1, and then D out now will be K. Now if I substitute this, H in is, so you see here H in the sense, now you should consider the pre-padded things. So this is 5 minus 3 plus 2, okay. Now this is 4 and this is 2. Now therefore this will be 3, this will also be 3, this is 2. So therefore the output will be 3 cross 2. Now using this we will be computing the output and the, so you given the input and these parameters that are there, now we can compute the output. Now let us verify now whether we have the same. Yes, you can say this 3 cross 2 is what you get, okay. So now that means that whenever you want to specify a convolutional operation, these are the things that you should specify. How many channels are there in the previous thing, how many channels, how many filters are there, which is nothing but how many channels are there in the output. Now what is the size of each of these filter or kernel, and then what is the stride and what is the padding. Now if you specify these, now you have specified a convolutional operation, okay. So now let us do that. So how do we do it? We use this what is known as nn.con2d, okay. So in channels is 3, how many input channels are there, out channels is 16, okay. Now these are, you can go ahead with that, and the kernel size is 3, So that means that you have a 3x3 kernel, and then since there are 3 channels in the input, so each filter will have 3x3x3, each filter will have 27 parameters, and then since you have 16 channels, say 16 filters like that, now you will have 27 into 16 plus 16 for bias terms. These are the number of parameters, and then the stride is 1 and the padding is 1. So now taking this, let's compute the output size. So now the H in that we have, so the input H in into W in into D in, so this is 32 cross 3 is what we have, and then what is the padding that we have? We have 1, stride is 1, the filter size is 3, K is 16. So now what will be the output size? So we want to compute the output size. Now D out is fixed, this is 16, okay, this is of no problem. So now H out equals H in, which is 32, minus F is 3 plus 2, wait a minute, I think striding is 1, pad is 1, okay, by S is 1 plus 1, okay. Now this is 29 plus 2 is 31, 31 plus 1 is 32. Now the output will be, so this is post the, you have a black box which is con 2D, the output will be 32 cross 16. Now this will be the output, okay. Now think of this, now once you perform this operation you can check for the shapes, you can see that now each of this example will be converted, the 16 is the number of channels, 32 cross 32, like that you have in a batch you had 8. Okay. Now always whenever we are performing the operation we will be considering the output with respect to one example, okay. Now this is the first is the batch size, so you have to keep it as it is. Now this 3 we had taken it as the last, and you can permute it perfectly fine. Now this is the first operation of convolutions. So these things you have to specify. You have to specify in channels, out channels, kernel size, stride and padding, okay. And then another important operation that we normally use whenever we look into the CNNs is the idea of max pooling. See, the idea of max pooling is to reduce the dimension, okay, and whenever the max pooling is used with max pooling 2D, that is you take a 2D as an input, kernel is 2 and stride is equal to 2. Now what happens is whenever you can do this case here, okay. So now if I go into the max pooling with the kernel size, which is in our case which we are referring F. Now if kernel size is 2 and stride is 2, how do you compute the output? The H in minus F plus 2P divided by S plus 1, this is how we do it, right, okay. Now what happens is this will go off, now there is no padding, so therefore this will be 0, okay. Now this is H in minus 2 divided by 2 plus 1. Now if this is 32, okay, 32 minus 2 is 30, 30 divided by 2 is 15, 15 plus 1 will be 16. So the input which was 32 is becoming 16. Now similarly for W also. So if you have an input which is 32 cross 32, post performing max pooling, now whenever I say max pooling I am specifically saying 2 cross 2, okay, wherein which the kernel size is 2 cross 2 and then the stride is 2. In this case, now what will happen is it will become 16 cross 16. Now if you have different options you can go ahead and use it, okay. So you can make stride is 1 and kernel is 3, that is perfectly fine. Now accordingly the shapes can be modified, but whenever we use, this is the standard configuration in which we use it, the size will be reduced by half, okay. So now here this is how you create an instance of this max pooling. So nn dot max pool 2D, the kernel size is 2, the stride is 2, there are no parameters involved here, okay. So in con 2D you had parameters involved, but in max pooling there are no parameters, it is just reducing the size by, in that 2 cross 2 kernel it is taking the maximum element which is there, which you can understand it by this example. Now this is you take a 2 cross 2 kernel in this case. Now what is the maximum element? The maximum element is 6, you get this 6. Now here the maximum element is 8, you get this 8. Now here the 3 and 4 accordingly. So what was 4 cross 4 has been reduced into 2 cross 2. Okay. So now so x dot shape what was 16, 32, 32, and then please remember, now it will not do anything for the number of channels. Okay. Now it is just out of sheer coincidence that this 16 you have 3 16s. Now if your input was some other thing, let us say that if input was 40, so then it would have been 20 20 in this case. Okay, it is sheer coincidence, there is no rule that these things has to be matched. Okay, fine. So now let us take a CNN example. Now here we are going ahead with the CNN which is 32 cross 32 and RGB image. Now that means that it has 3 channels. Okay, the input is a 32 cross 32 and then it has 3 channels. Okay, now therefore now let us look at this convolution one. Now the input is a 3 channel, that you are converting it to a 16 channel, the kernel is 3, padding is 1. If you have not specified the stride, now by default the stride will be 1. Okay, if you have not specified the padding, by default the padding will be 0, there will be no padding. Okay, and then you have another convolution and then you have a pooling. See here in the init method, so this is a simple CNN, it has to be a child of nn dot module, the same story that we did for MLP holds good perfectly well here. Okay, so the number of classes you have 10. So now after that you have fully connected layer, now which is, this is the input, this is the output 28. So this is 32 into 8 into 8 nodes to 128 to 128 to number of classes. Now let us compute this, how is this happening? Now the first x, now what is the input of this? So the x that you have, the input is it is 3 cross, okay, so it is 3 cross 32 cross 32. Okay, this is the, so this you are passing it through the con 2D which is having parameters 3, 16, kernel is 3, padding is 1, stride is 1. This is in channels, out channels, this is K, this is F. Okay. So now then, now we can perform the operation. So what will be the output of this? So the output of this will be 16 cross 16. Why 16? Because your K is 16, therefore the number of channels output will be 16. So this is 32 minus 3, okay, plus 2 divided by 1 plus 1. So this is 32 minus 3 is 29, 29 plus 2 is 31, 31 plus 1 is 32, this is 32 cross 32. Okay, this will be the output size of this con 2D. This which you have, okay, see you apply ReLU, see whenever you are applying ReLU, see ReLU is applied individually, so it will not change the dimension, so I keep it as it is. That you are passing it through a max pool. So whenever, what is the max pool? Kernel size is 2 and stride is 2. Now therefore whenever you pass it through the max pool, the output will be 16 cross 16 cross 16. Okay, this is the output. Now then you are passing it through a convolution 2D, sorry, second convolution, which is 32 16 3 1. Okay, now this you are passing it through another con 2D. Now wherein which 16 is the input, K is 32, F is 3, P is 1, S is 1. So in this case, now what it will be? So the output will be 32 is fixed. Okay. Now this is 16 minus 3 plus 2 divided by 1 plus 1. Now this is come to 16. So therefore this is 32 cross 16 cross 16. okay, and then whatever you have, this you pass through the max pool. Now once you pass through the max pool, it is 32 cross 8 cross 8. This is the output that you have got post your operations of CNNs. Okay. So now, so whenever you perform this 2 convolutions, now you would have 32 cross 8 cross 8. Now what do? You convert it into a vector. Now you have to take a decision. Okay. Whenever you want to take a decision, so the output is a vector. Okay. Now you have to convert whatever the features that you have extracted into a vector. Now whenever you convert this into a vector, see this size will be, the number of nodes here now will be 32 cross 8 cross 8. Okay. Now this has to be converted into a, we use a fully connected layer. So this is what is known as flattening. X dot view, you take this whatever is the size 0 of it, now you convert it into a vector. Okay. Now then 3288 to 128. Now that means that here you have 128 nodes, and then 128 to number of classes. Okay. Now the number of classes I have said as 10, so it will be 10 here. Now you pass through this, and then this output that you get here, now this is logits. Now finally you can pass it through the softmax to get probability of y given x is equal to x. Now this is a probability vector which is in R10. So wherein which the first element says that what is the probability that y is equal to 0 given x is equal to x, till probability that y is equal to 9 given x is equal to x. Now then what do? You take the argmax of this, that will be the decision, which is nothing but your y hat or y prediction. Okay. This is the overall full story. So that is what is being done here. Okay. Now we can see these shapes. You have created an instance of it with 10 classes. So you have created an example with 4 as the batch size. Now this is the 3 dimensions for each example RGB, 32 cross 32. So this dummy input you are giving it through the output. After the convolution, the first convolution, the output is 16 16 4. This 4 is the batch size, has to be there as it is. Now after the first convolution plus spooling, so the first convolution plus spooling, so that means that this is the output that I got. Okay, 16 cross 16 cross 16. Now 4 is the batch size, so it is matching. And then the second convolutions and then the pooling, which is this. Oh sorry, no, not this. Which is after convolution. This is after pooling, which is 3288 is what I got. You can see 3288, and then once you flatten it out, 3288 will become a vector of 2048. Now that 2048, now this is 2048. Now whatever is in 2048 dimension, you have taking it into a 128 dimension, and then you are putting it into 10 dimension. So which is your logits in this case. Okay. So which is 4, all the 4 examples 10. So how it will be? Now you will have the first example, the 0th example, you will get a probability vector. The first example you will get another probability. The second example get another probability vector. The third example you get another probability vector. Okay. Now each one of this will have 10 elements. This is a 4 cross 10. Okay. Now this is the same thing without what do you call any prints, so that we can use it. Okay. So now let us look at how do you get the data set. Now here we are going into the case wherein which the data set that we are considering is present in the PyTorch repository itself. So now how do you get it? Now you want to use this torch vision. this is the thing, and then whatever input that you have got needs to be transformed. Okay. So now what do you mean by transformation? See, the input that you get, so maybe in the format of NumPy or so, that needs to be converted into a tensor. Okay. Sometimes you might want to resize it, sometimes you want to introduce couple of other regularization ideas, now which we shall be looking at somewhere down the line. What are the different regularization ideas that we can think into. Okay. So now those are the transforms. So you compose, you bring in all the transformations together. Now first you are converting it into a 32 cross 32. See, MNIST which is there is 28 cross 28. You are just extrapolating it into 32 cross 32. Now the reason why I am doing it is, see, initially I wanted to show it on a 3 channel image which is CFR10. Okay. It took exactly too much of time to download, so I just transformed the same data which is there into a do it for MNIST. So MNIST is easy for us to download. See, going on most of our generative models, now we will be using MNIST only for 2 reasons specifically. Now one is it is of small size. So another is, so you will not burn too many GPUs. Okay. Now this Google Colab which we will be using throughout. Okay. Now it allocates certain amount of GPU for you. So we actually do not want to use it too much. Okay. For that specific reason, now what we shall be doing is we will be going ahead and using MNIST for most of our thing. Somewhere down the line we will be using some small emojis data set also, which we will look at sometime later, perfectly fine. So once you have resized it, that you are converting it to a tensor, that is what line number 10 is doing. Okay. Now how do you get the data set? From Torch Vision data sets, you are getting the MNIST. Now where is this data? So okay, now you are storing this data in this from the current working directory in data folder. See, sometimes you might have the data already ready with you. Okay. In that case you do not need to download it. Now else you might need to download it. Okay. So now you have this root in this place. Now you are only getting the training data, that is why the train is true, and then download is equal to true. That means that in the specified location, if the needed data is not there, you can go ahead and download it. That is what is being done here. Okay. And then post that you apply this transformation which is there. Now what is the transformation? You convert it into a 32 cross 32 size and then convert it into a tensor. Okay. Now this is your training data. The same thing with your test data as well. Now you will put it into the same folder. Training is false, now indicating that we are looking at the testing data, and then download is equal to true. That means that in the specified location, if the data is not there, you go ahead and download it. Now you apply the similar transforms. Okay. See, most of the times so we will have a similar transforms for training and test. Now one thing that needs to be taken into consideration in both the cases is the size. Now whatever is the size of your input data, the same thing has to be the size of your test data as well. Okay. Train and test data should be of the same size. Okay. So then you are creating the data loader. Now this is data set is done. Okay. Now you are creating a data loader using this data set, now in which it is an accumulation of all the data. So now the batch size is 64. Okay. In each batch you will be going ahead with 64 examples, and then the shuffle is true. The same thing with the test. See, in the test you can have a different batch size, that perfectly fine. Okay. In the test you do not need to shuffle because you will be running it only once. Okay, to the case. And then how many train data set classes? Now will give us the total number of classes that are there. Okay. So and then what is the length of training data? You have 60,000 examples. In the test data you have 10,000 examples. Okay. Now 0, 1, 2, these are the different classes that are there. Okay. This is regarding the MNIST data. See, we can use any other data set as well. You can use FMNIST, you can use CFAR. FMNIST is easy to download, but CFAR it will take some time, even though if it is around 170 MB, so somehow it took a lot of time. Okay. So now let us visualize some of them. Okay. I will not go ahead and explain this visualization plot. Now these are the images that are there. Okay. Now this is coming in color. Now the reason why it is coming in color is I have not transformed it to take a grayscale image. You can transform it, but the input is grayscale. Okay. The input is not a 3 channeled image. Okay. What happens is this matplotlib which is there, now it will automatically convert any grayscale image as an input, it will automatically convert it into a 3-channel thing, it will just repeat the same thing for the remaining 2 channels. Okay. That is what it does unless specified. Okay, you have to specify it, do not do it, okay, which I have not done in this case. Now as a why, the reason as I told you, my initial aim was to work with C for 10, somehow it did not download, okay, fine. So now let us go into the training aspect. So the model, you create this instance, so the number of classes that you have is 10, so and then you are porting it onto the device. So you are using cross entropy loss, the optimizer that you are using is Adam. So with the learning rate of 0.001, okay, the same old story, the training procedure is exactly the same thing, you are doing it for 5 epochs. For each epoch you put it the model in the training mode, running loss, correct and total, you compute exactly the same story that we used earlier for binary classification. So but there what you did was all the examples were taken at once, okay, but here what happens is you cannot take all the examples at once, you have divided them into batches. Now therefore you have to do it batch wise, so therefore you have to iterate over the train loader. Now at each time it will give you the images and their respective labels, you convert them onto the you port them onto the device, perform the forward pass, compute the loss, optimizer.0grad, okay, clear off the previous gradients. So loss.backward, compute the gradients for the new batch, optimizer.step, based on those gradients go ahead and update the weights. So and then running loss, prediction, everything the same old story. So see, I just want you to bring it into your notice that in one epoch there can be multiple updations of weight, okay. So for the first batch you take some W and then you update it, for the next batch you will be using this updated weights, okay. So it is not like earlier examples wherein which for each epoch your weights will be updated only once. So in this case for each batch there will be a weight update, so please keep it clear, okay, for each batch there will be a weight update which will be considered, okay. So that means that the number of weight updates is, now how many batches are there into how many what do you call epochs were done, okay. Epoch, whenever we mean epoch, it is run through the whole data once, okay, that is what we mean by epoch, you run through the whole data. So whenever I mean whole data, the whole of training data, the whole of 60,000 samples that we have. Whenever we mean iteration, now we mean that it is updation of weights once, okay, fine. So you just do it, so post 5 epochs you are getting 99% accuracy. See now this MNIST is a beaten data, okay, so you will find it for every example. It is like first, see whenever you take a calculator, no, normally what do you do, so even though you know the outcome, so you just try it whether the calculator is working or not, you just put some 2 plus 2 or 1 plus 1 or 1 plus 0 depending on your favorite number, you just put that, no. So MNIST is like that, so it is for sanity check. If your data is working well on MNIST, sorry, if your model is working well on MNIST data, so that means that it is working, okay, it is just sanity check. If it is working, it is working perfectly fine, no problem. Okay. Now then you can think of, okay, extending, okay, now can I go into another data sets, that is how all of us work. First we try on MNIST data, now because of high availability of GPUs, now people have stopped it, but the main usage is first you try it on MNIST, if it is working on MNIST, okay, you can try it on others, okay, that is the bare minimum, it should work on MNIST, fine. Now this is training aspect. Now how do you perform the evaluation? See now please remember this, the evaluation metrics that are there. Now how do you evaluate a model? So in the regression tasks that we will be doing, the loss function can also be used as an evaluation metric. For example, the loss that you will be using, which is MSE loss, can also be thought as an evaluation matrix. But in classification kind of tasks, that is not true, okay. So the evaluation matrix that will be used is accuracy, but whenever you have skewed data, now we will go into other metrics like precision, recall, F1 score and stuff. So I am assuming that you are quite aware of all these different evaluation metrics. Now else you can find ample resources available online. Okay. So fine, the evaluation metrics, since it is the MNIST data that we are using, which is a balanced data. What do you mean by balance? Each class has same number of examples. Now we will not be going ahead with precision recall. Now we will be just going ahead with the standard accuracy. So to compute accuracy, what is accuracy? Total correctly classified examples divided by total number of examples. So that for the test set which is there, you should have a counter, wherein which you keep track of all the correct examples, and then you go into how many number of total examples are there. So now here we go ahead with evaluation mode. Okay. So earlier we went with the training mode. So this is the evaluation mode. So whenever we are going ahead with evaluation mode, we will not be going ahead with any kind of gradient tracking or gradient computation. You do not need any of them. So you have the fixed weights that are there, you just perform the forward pass, take the decision and then see what is the total what do you call examples that are correctly classified and report the same. That is the idea. So you have this bookmarkers correct and total for the same. So with torch.noGrad, so that means whatever is inside this block, you will not be going ahead with any kind of gradient computation. See again, so you do not need to do it for multiple epochs, not needed. Okay, evaluation is only done on the test set once. Now that is the reason why while creating the data loaders, you did not give shuffle is equal to true. You can give, okay, we made shuffle is equal to false, it is perfectly fine, but not necessary. Okay. So images, so always first you have to port it onto the device. So perform the forward pass, you get the logits. So take the argmax of those logits in dimension 1, that is with respect to column. Now why, now again see here, now you want to go ahead and find the argmax with respect to this for the elements of this column, right. Therefore you go ahead with dimension is equal to 1. So whatever is the argmax, so that will, so your y prediction will be like some 4, okay, so it will be, sorry, so now let me write it, so it will be, this is for the first example, second example, third example and fourth example. So you get like that, and then so this is also a row vector prediction, labels, this is also a row vector. So you find what are, how many examples are there equal, and then you take the sum of it, convert it into item, the standard thing, and then you go ahead. The test accuracy that you have got is 0.98. Okay. Now please remember that the training accuracy and test accuracy can vary. Okay. So I am assuming that all of you are very much aware of the training laws, the test laws, the training accuracy, training metric, and then the test metrics and other things. Okay. So now this is regarding CNNs. Now this is where we stop at this moment. Now to give you a recap, what did we look at in this section of tutorials? We looked at the convolutional neural networks, how they work, how the computation of convolutions happens, how do you given an input size and then the hyperparameters of that specific convolutional operation, how do you go ahead and compute the output size, and then we put all of them together, the feature extractor which is convolutional networks, and then the classifier head which is there, we put them together to take a decision. Okay. Now this is what we have discussed till this point. Now in the next section of this tutorial sequence, now we will be looking at how do you work with sequences. Okay. So there we will be looking at RNNs, LSTMs and GRUs, and then we will be coming up with an RNN and LSTM classifiers. So that is where the next batch of tutorials will end, and then after that we will see how can we load the pre-trained models, and then how can you work with the pre-trained models, and how can you modify. So we will take an example wherein which we take a pre-trained ImageNet example, and then we will work on MRI data. We will see that example down the line. Now with this we conclude today's tutorial. I hope it was helpful, you enjoyed it. So meet you in the next section wherein which we will be looking at sequences. Thank you. Bye.